All right, let's dive into the big one, electricity and DC circuits for 9702 physics. You know, that section of the exam that can really make or break your grade? The one filled with all those tricky multi-step problems? Well, stick with me because we're about to turn this whole topic into your secret weapon.
First things first, why should you care so much about this particular topic? Well, how about this? It accounts for roughly 20% of your entire AS physics exam. Yep, that is a massive slice of your grade, which means getting this right is pretty much non-negotiable if you're aiming for a top score.
And look, I get it. I know what so many students call this, the horrible section. But what if I told you that all those tricky questions are just the same few patterns wearing different disguises? Today, we're going to pull back the curtain and simplify everything, from drift speed to potential dividers, using the exact shortcuts and methods that reveal those patterns.
So let's start at the beginning by cracking the code. These fundamental ideas are the absolute building blocks for every single circuit problem you're ever going to face. If you can get these right, you'll find that the harder questions, well, they almost start to solve themselves.
First up, quantize charge. Now this sounds really complex, but I promise it's a super simple and powerful idea. All it means is that charge isn't like a smooth, continuous flow of water. Nope. It's more like a stream of tiny, identical Lego bricks. You can have 1 brick, 2 bricks, or 1,000,000 bricks, but you can never, ever have half a brick. Each one of these bricks has a value of E, the elementary charge, so any charge you ever find has to be a whole number multiple of that value.
So how does this actually show up in an exam? Usually just like this. They'll give you a multiple choice question and ask which charge is possible. Here's the trick. You don't need to do any crazy calculations. You just take each option and divide it by the value of one of those Lego bricks, that 1.6 times 10 to the minus 19. Only one of the answers will give you a perfect, clean, whole number. In this case, option C gives you exactly 7. It's the only one that can physically exist.
Okay, this next one, you need to tattoo this equation on your brain. It's the big one for current. I equals A N V Q. You have to know what every single letter means. I is the current. A is the cross-sectional area of the wire, you know, how thick it is. N is the number density, how many charge carriers are packed in there. V is their drift speed, and Q is the charge on each carrier, which is almost always just our friend E.
Now here's a really common exam question that trips people up. They'll ask for the number of electrons in a piece of wire, but they won't give you A or N. Sneaky, right? But there's a simple 3-step workaround. Step 1. Find the time it takes for an electron to travel that length. Just use time equals distance over speed. Step 2. Use that time to find the total charge that flowed past. Q equals I times T. And finally, step 3. Take that total charge and just divide it by the charge of a single electron. Boom. A high-yield question solved with simple steps.
And that leads us right into a classic examiner trap. Imagine a current flowing through a wire that suddenly gets way thinner. Now, in a series circuit, the current I has to be the same everywhere. It's got nowhere else to go. So if you have the diameter of the wire, the area A actually decreases by a factor of 4, because area is proportional to the radius squared. So for I to stay constant in our I equals ENVQ equation, the drift speed V has to increase by 4 times to make up for it. They love, love, love to test this. Okay, let's move on and build on that. Now we're looking at resistance, and maybe more importantly, those really common traps and graph questions that can rob you of easy marks.
Before we can talk about resistance, we got to talk about its cousin, resistivity. Here's the key difference. Resistance depends on the shape of a component. Is it long? Is it thick? But resistivity is all about the material itself. Copper has its own resistivity, iron has another. The formula you need is R equals rho L over A. Basically, the longer the wire, the more resistance. The fatter the wire, the less resistance. Simple as that.
Right, you absolutely must be able to recognize and sketch the IV graphs for these 3 components. For a standard metallic conductor, it's just a perfect straight line right through the origin. That's Ohm's law. A filament lamp, though, is different. Its graph curves over because as more current flows, it gets hotter, and a hotter wire has more resistance. And finally, the semiconductor diode. Just think of it as a one-way street for current. It lets electricity flow easily in one direction, but it's a total roadblock in the other. And here's another classic trap question. If you stretch a wire to double its length, what happens to the resistance? Your gut might say, oh, it just doubles, because R is proportional to L. And that's exactly what the examiner wants you to think. But it's wrong. Here's the key. When you stretch a wire, its volume stays constant. So if you make it twice as long, you're also making it half as thick. Looking back at our formula,
R equals rho L over A, you've doubled the L on top, and you've halved the A on the bottom. The total effect? The resistance actually increases by a factor of 4. Okay, now for the tools that will let you solve pretty much any DC circuit, no matter how scary it looks. Let's talk about Kirchhoff's laws, and please don't think of them as complicated rules. Think of them as powerful shortcuts.
Kirchhoff's two laws are actually just basic conservation principles in disguise. The first law is simple. At any junction in a circuit, the total current going in has to equal the total current coming out. It's just conservation of charge. You can't create or destroy it. The second law says that if you go around any closed loop, all the energy supplied by the batteries has to be used up by the components. That's just conservation of energy. See? Not so scary.
And while we're on the topic of shortcuts, here is a massive time saver for your multiple choice paper. When you have exactly 2 resistors in parallel, don't waste your time with that messy 1 over R formula. The total resistance is just their product divided by their sum. R1 times R2 over R1 plus R2. Memorize it. It is so much faster.
Okay, this is where we level up to the pro-tier techniques. Potential dividers, especially the ones with thermistors or LDRs, are where you find some of the toughest qualitative questions. But of course, we have a hack for that.
But first, a quick word on internal resistance. See, real batteries aren't perfect. They all have a little bit of resistance inside them. The voltage you actually get out of the battery terminals, V, is its total energy, E, minus the voltage that gets lost inside the battery, which we call lost volts. The key thing to remember is this. The more current you draw from the battery, the more volts get lost, and the lower the voltage it can supply to your circuit. Now, check out this classic exam question, a potential divider circuit with a thermistor. And the question is always something like, what happens to the voltmeter reading if it gets colder? Now, you could try to reason it out in your head, but that's where you make mistakes when you're under pressure, so let's use a bulletproof method instead. This is the substitution method. Instead of thinking in abstracts, we're going to use easy numbers. Step 1. Pretend the battery is 10 volts and both resistors are 10 ohms. The voltage splits evenly, right? So the voltmeter reads 5 volts. Okay. Step 2. Change a value based on the question. It gets colder. We know for an NTC thermistor, its resistance increases. So let's just say it goes up to 30 ohms. Step 3. Recalculate. The new total resistance is 40 ohms. The new voltage across the bottom resistor is 2.5 volts. So what happened? The reading went from 5 volts down to 2.5 volts. It decreased. See that? You've turned a confusing word problem into a simple, certain calculation.
So we've covered the physics, we've covered the hacks, now let's talk strategy. Because knowing the content is only half the battle. You need a solid game plan for the exam itself. Think about it. In the multiple choice paper, you get 40 questions in 75 minutes. That works out to 112.5 seconds per question. Less than 2 minutes. Time is your most precious resource, and you have to manage it absolutely ruthlessly.
So here are your pro techniques. First, if you see a circuit diagram that looks like a total nightmare, do not get bogged down. Circle it, skip it, and come back to it at the end. Second, use elimination. Before you even start calculating, look at the answers. Are the units wrong? Is a power of 10 obviously out of place? Get rid of it. And finally, pay super close attention to the command words. Calculate just wants the final number. Show means you have to write down every logical step. And explain means you have to write a sentence using physics principles.
So, what's your next step? Practice. The single best thing you can do now is find some recent October/November past papers. They are almost always a perfect conceptual match for the kind of thing you're going to face. Find them and apply every single technique we've talked about today.
So there you have it, the strategies and the shortcuts you need to master electricity. Just remember, these are powerful tools to help you, not replace your learning. So make sure you revise the entire 9702 syllabus thoroughly. Go into that exam with confidence. Good luck. You've totally got this.